All right, Chemistry 3111. This is Chapter 13, which deals with ethers and epoxides, thiols, and sulfides. Let's start by taking a look at the functional group. An ether group includes an oxygen atom that is bonded to two alkyl groups, or they could be two aryl groups, but anyhow here we have an ether, so we have an R group, and then we have an oxygen sandwiched in between these two R groups like this. Now the R groups again can be alkyl, they could be aryl, or they could be vinyl groups. They can't be acyl groups. And if you're wondering what an acyl group is, an acyl group is when we have a carbonyl, okay, with an R group attached to it like that. And as you can see, if you were to replace one of these R groups with the acyl group here that I have drawn in red, then you'd end up with an ester, okay? And so this down here is an ester. This is not an ether. And so again, an ether is when we have two alkyl, aryl, or vinyl groups with an oxygen in between them. An ether is a common functional group that's found in many natural products and synthetic compounds as well. For example, in terms of the natural products, morphine is a natural product, and you can see that there's an ether right here. We also have other functional groups like alcohols, and we have a tertiary amine over here. We have an alkene too. Anyhow, and then it's also found in synthetic compounds like Prozac. Here is the IUPAC name, which is R-fluoxetine, and you can see that there's an ether right here in the compound. It also has an amine here and some aromatic rings. Anyhow, so ethers are very common in natural products and synthetic compounds as well. Of course, before we get into the chemistry of ethers, we have to talk about how to name ethers, or the nomenclature of ethers, and we're going to look at common names and IUPAC or systematic names. Now the common names for ethers, what we do is we name each R group and then we arrange them in alphabetical order, and we just put the word ether at the end. So you can see this first example here, we have an ethyl group, right? We have an ethyl and we alphabetize that according to the letter E. And we have a methyl group over here and we alphabetize that according to the letter M. And so this becomes ethyl, methyl, and then ether. So ethyl, methyl, ether. Here's another one. We have a tert-butyl group on the left side, and we have a methyl group on the other side. Now remember, we ignore all prefixes except iso, cyclo, and neo when it comes to alphabetization. Tert is not one of those prefixes, and so we ignore tert, and we alphabetize this group according to the letter B for butyl and M here. And so the name of this compound, the correct common name would be tert-butyl methyl ether. I just want to point out something that's mentioned in the book is that the acronym that's commonly used for this compound right here is MTBE, which is methyl tert-butyl ether. And methyl tert-butyl ether, which again is the incorrect way of naming the compound, this was used as an additive in gasoline for many years, but then it was found as a contaminant in groundwater, and so it was phased out. But it's also used as a solvent for extracting organic compounds in the lab. So still used for that, however, not used in gasoline as an additive. For the IUPAC or systematic names, what we do is we find the longest or the largest R group, and we call that our parent chain, right? Just like we did in alkane nomenclature or alkene nomenclature or alkyne nomenclature. And then it says here the second rule is that the smaller R group is called an alkoxy substituent. And if you're wondering what's an alkoxy substituent, I'll show you some examples. Let's say we had a methyl and an oxygen like this. We would call that a methoxy, right? A methoxy. Let's say you had an ethyl group and an oxygen like this. We'd call that an ethoxy. And we can keep going. Let's say we had an isopropyl group and an oxygen like this. We would call that an isopropoxy. We could keep going, but we'll stop there. Anyhow, so again, we have our parent. That's going to be our longest carbon chain, and then we name the other part as an alkoxy substituent. Here's an example of a compound that we're going to name using IUPAC nomenclature. You can see that the longest carbon chain has 1, 2, 3, 4, 5 carbons in it, and so it's some kind of pentane. But you can see that on carbon 1 we have an ethoxy group, right? Because we have CH3, CH2, so this is an ethoxy, just like I drew up here. And so the name of this compound would be 1-ethoxy pentane. So that would be the IUPAC name for that compound. Let's try naming some compounds using the IUPAC rules. We'll start with the first one here. We're going to find the longest carbon chain, which has 1, 2, 3 carbons in it like that. So this must be some kind of propane. And then on the second carbon here, we have an ethyl group with an oxygen attached. So this is an ethoxy group, an ethoxy. So this compound must be 2-ethoxypropane like that. Let's give the next one a try. We do the same thing. We find the longest carbon chain, 1, 2, 3. The reason I started numbering with this carbon here instead of this carbon is because my groups are going to be at carbons 1 and 2 as opposed to 2 and 3. And so there's our longest carbon chain. So this must be, again, some kind of propane. We're hooked on the propanes here. So some kind of propane. What else? We have an ethoxy group on carbon 1. So we have a 1-ethoxy. But we also have a 2-chloro. And so when you put all that together, you would have 2-chloro, right? Because C comes before E in the alphabet. So 2-chloro, 1-ethoxypropane, like that. And now we have to assign the stereochemistry at our chiral center. Well, let's take a look at that. We have a hydrogen in the back that's going to be our lowest priority. We have the chlorine that's going to have the highest priority because it has a higher atomic number than any other element in this molecule. If you look at this carbon, it's attached to an oxygen, hydrogen, hydrogen, and the methyl group is attached to hydrogen, hydrogen, hydrogen. And so here is our tiebreaker. So we go from 1 to 2 to 3 like this. And so if we follow going around like this, that's counterclockwise. And so this molecule, the correct name would be S2-chloro 1-ethoxypropane. And finally, let's take a look at this one. You can see that the longest chain is the 6 carbons in the benzene ring. So this must be some kind of benzene, and we have an ethoxy group here. We don't have to give that ethoxy a locant because an ethoxy or an ether has a higher priority than the 2 chlorines. And so this must be some kind of ethoxy benzene. And if we number it so that we give the first chlorine the lowest possible number, so 1, 2, 3, 4, this molecule becomes 2,4-dichloro ethoxybenzene. What about the structure and property of ethers? It says here that the bond angle in ethers is very similar to that found in water and in alcohols. So it must be close to the tetrahedral bond angle, which is 109.5. Also, you should be aware that the oxygen of an ether is sp3 hybridized, and hybridization is something that we looked at in general chemistry as well as the first chapter of Organic Chemistry 1. It says here that the larger the R group in our ether, the wider the bond angle. So if we look at the examples down here, you can see water has a bond angle that's a little bit less than 109.5 degrees, and that's because of the repulsion of these two lone pairs here. They kind of repel each other and they push the hydrogens towards each other a little bit. But once you put a methyl group on here, and methanol, right, because of the size of this methyl group, it kind of pushes the methyl and the hydrogen away, and we have a bond angle of around 109 degrees. And then when you have dimethyl ether, so now you got 2 methyl groups that are going to repel each other sterically because they're pretty big, and so they're going to push each other away, and we have an even bigger bond angle. And that goes right along with what it says here. The larger the R group, the wider the bond angle. Something else you should be aware of is that alcohols have relatively high boiling points as a result of hydrogen bonding, and this is something that we learned a long time ago, but alcohols we discussed in chapter 12, and you can see some hydrogen bonding shown here between 2 alcohols. You should know that you should draw the hydrogen bond as a dashed or dotted line between the lone pair on an oxygen and the hydrogen of another alcohol here, and the reason why is because that oxygen is partially negative, right, because it's more electronegative than hydrogen, and that renders the hydrogen of a hydroxyl partially positive. Anyhow, ethers can only act as hydrogen bond acceptors. So the ether here is a hydrogen bond acceptor, right? Because it's accepting the hydrogen bond from the hydrogen atom of an alcohol shown here. Okay. Now, if you have a pure sample of an ether, there's going to be no hydrogen bonding, right? Think about it. If you have a pure sample of 2 ethers, right? If I just draw 2 ether molecules, just keep it nice and simple here. I'll try to draw the correct geometry here. My my bent geometry. Anyhow, there's no way that I can draw a hydrogen bond between these two ethers that I have inside this blue box, right? You've got to have a hydrogen bond donor, right? Because here the hydrogen bond donor is an alcohol. This is just rehashing what I just said, in that ethers cannot hydrogen bond amongst themselves, and so their boiling points are going to be much lower than alcohols of comparable size. And if we look at these compounds here, ethanol, dimethyl ether, and propane, they all have similar molar masses, but you can see that the boiling point of ethanol is much higher than that of dimethyl ether, and that of dimethyl ether is higher than that of propane. And the reason why is because the only intermolecular forces that propane is going to experience in a pure sample are London forces, right? London forces, whereas dimethyl ether, there is a permanent dipole in here, and so dimethyl ether will experience dipole forces and London forces. Then you go to the alcohol, and not only does it have those two intermolecular forces, but it also has hydrogen bonding. So it has hydrogen bonding, which is the strongest of all the intermolecular forces, as well as dipole forces and London forces. So that explains why the boiling point increases as the intermolecular forces get stronger. What else? It says here that the larger the ether, the higher the boiling point. And the reason why is due to the increased London dispersion forces. And if you think about it, if you put another ether here, let's say next to diethyl ether, you can see that there's going to be an increased amount of surface area in contact between these two molecules than there would be, say, if I had two molecules of dimethyl ether. Right? So just the longer that ether is, the more opportunity there is for London forces, and the higher the boiling point is. And that shows you why, or explains why, as the ether gets longer or larger, the boiling point increases. Ethers are commonly used as solvents in organic reactions. Diethyl ether is used in all kinds of different reactions. In fact, we used it in Greenyard chemistry quite commonly. But the problem with diethyl ether is that it's highly flammable, and it's also quite volatile. That means it has a pretty low boiling point. And THF, which is tetrahydrofuran, is even more widely used as a solvent in organic chemistry because it's not as volatile, meaning it doesn't evaporate as quickly, but it is easily removed from a reaction mixture. Dioxane is also sometimes used, and you can see that that has two ethers in it. And sometimes dioxane can be used for what's called lyophilization, which is basically freeze drying an organic molecule to make it or convert it into from a crystalline solid into an amorphous solid. Anyhow, again, ethers, relatively low boiling points, and that's because they only have dipole forces and London forces, no hydrogen bonding, and also they're fairly unreactive, okay? And that's to the advantage of an organic chemist when she or he is trying a reaction with, strongly acidic or basic conditions.